Hello. Okay, let's solve this problem. I share the link. It's a hard tree problem. We are asked to find the kth ancestor of a tree node. But it is a query problem. We are given the tree at the beginning, and then we are asked queries about nodes and the kth ancestor. So the tree is static, which is one type of query problem. So yes, we're given the tree as a parent array. No worries, we just started. And for every node I from 0 to n-1 inclusive, we know which one is the parent. The root of the tree is a node 0 that doesn't have a parent, so we get -1 as the parent of 0. And so the kth ancestor of a tree node is the kth node in the path from that node to the root node. Hey, Roy, thanks for the follow. And so we need to answer these queries, and if there is no such ancestor, we have to return -1. And we have one example. Here they ask us, so this is the tree, and they ask us for the ancestor of node 3. The one ancestor, first ancestor, which here we can see it is 1. So that's why it returns 1 in that case. Then the second ancestor of 5, which is the root 0. And then we're asked for the third ancestor of 6, which is not part of a tree. It only has 2 ancestors. So that's why in this case we have to return -1. And yes, and that's the only example. So notice that the ancestors of a particular node they form a line in a sense. So when we think about the ancestors of a node, we can forget about the tree and just think about a line that goes from that node to the root. So the technique that we can use to solve this problem is called binary lifting. And the idea is to pre-compute a table. So we want to pre-compute the kth ancestor for every node in the tree, but we want we are going to restrict ourselves to k's that are powers of 2. Okay, so that would be 2 to the 0, which is 1, 1, 2, 4, 8, and so on. Because there are not that many powers of 2 that satisfy these conditions. And then we can respond the queries if we decompose. When we're given an arbitrary k that is not a power of 2, we can decompose it into powers of 2. And we can make the jumps. If we have the information of what is the kth ancestor for the powers of 2, we can make all those jumps and we can get quickly to the answer. Why quickly? Because the number of powers of 2 that compose a number depend on the number of binary digits that the number has, which will be small. In this problem, the number of nodes and k can be up to 50,000. So let's see how we can compute the powers, the ancestors for powers of 2. So like I said, we only care about lines here. So I'm gonna draw the line vertically so that we can think that it is a tree, but it doesn't matter. I guess the arrows should be pointing upwards because we care about the parents, but it doesn't matter. So let's say that we have this node A, and let's say 1, 2, 3, 4 that we want to know what is the 4th ancestor of A. So we want to make a jump of 4. So 1, 2, 3, 4. But a jump of 4 is composed of jumps of 2 jumps of 2, right? We can jump here and then we jump here. So if we want to know what is the 4th ancestor of A, we can find the 2nd ancestor of A. Let's say this is B. And then we find the 2nd ancestor of B, and that is going to give us our answer. And notice that this is true for every power of 2. For every power of 2, we can compose it of 2 times the previous power of 2. So in terms of the table that we want to compute, let's say that we have a table called ancestor, and first we're going to say what is the 4th ancestor of the node A. Okay, and this is just translating what I said to code or to and here we want the 2nd ancestor of what? Of the ancestor, also the 2nd ancestor of A. Okay, so this is jumping 2 times. This is going to be B. So if we compute this in order of the powers of 2 from smallest to largest, when we want to find the 4th ancestor, we are already going to have the 2nd ancestor. So that's why this is a kind of DP. By the way, this is here I'm using the power of 2, but since these are all powers of 2, we can instead of writing 4, we can use the exponent. So 4 is 2 to the 2, so we can just, in this case, put 2, and here we would write 1 and 1, but it's the same. So yes, that's the idea. It's very simple if you think about it. I mean, I guess you need to know the technique to figure this out, but once you know this idea, it's pretty simple. So one question is, what size does the table has to be? So the maximum k that we are going to get is, like I said, 5 times 10 to the 4, and I guess I can explain how to do this quickly. So you should know that 2 to the 10, so this is not approximately, this is equal, but 2 to the 10 is approximately 10 to the 3. So this is separated. So here this is 52, and the biggest power of 2 that does not exist 50 is 2 to the 5, so 32. So the biggest power of 2 that we are going to decompose k into is going to be 2 to the 15. So that means that our table has to be from 0 up to 15 inclusive. So the number of bits that we need is going to be 16. Okay. So without further ado, let's code it. So let's make the ancestor table that we talked about. The size is going to be bits in the first dimension, and in the second dimension it's going to be n. And notice that for the when k is 1, so when the exponent is 0, the ancestor is going to be the same as the parent. So I think we can do this, and then we want to go, so let's call this, what's your contest rating? Let me finish this. So let's say the exponent goes from, we already took care of 0, so let's start from 1. We want to go from smaller to largest so that we can use that recurrence. And this is just copying what I wrote here. So the ancestor of E of, okay, so we need to go over the nodes. Let's call this node I. So the ancestor E of I is going to be the ancestor E minus 1 of the ancestor of E minus 1 of I. And that should be it. So this has to be part of the class. And I don't think we need to remember anything else from the parameters. And now we want to decompose k into powers of 2. So we want to know if k has this bit on and we want the node to be the ancestor I of the node. So here, this means that k is composed of the ith power of 2. So that means that we want to make a jump that is 2 to the I. And that is from the current node. So that is what our table gives us. So we make a jump and now we have our new node. And finally, we return the node. Let's see if I coded correctly. Okay, I forgot to use this. And it passes the example. Let's see if it works. Oh, whoa, whoa, whoa. Got a wrong answer. Can you explain 12? This? Well, there is a bug, so I wasn't expecting to have a bug. What is this? How can we see? Is there, sometimes they show you a tree, drawing of the tree, but I guess not in this problem. So why I found these results hard to. What is this null? Is this a response to the constructor call? I guess. So you always start with null. And we are getting a -1, no, a 0 when we had to respond -1. Okay, let me explain it to see if I can find the bug. You want me to explain this method, right? So we said that we wanted to decompose k into powers of 2. So what we are doing is we are considering all the powers of 2 that okay. We are going over so what was the k here? So k is 5 here. Why can't you just return? No, because k has to be, we only pre-computed the ancestors for powers of 2, and k is not necessarily a power of 2. We have to break down k into powers of 2 and do those jumps. So here, so in binary, 5 is this. This is bit. This is, I don't know how to use this. This is bit 0, bit 1, bit 2. So I'm going over, so my variable I goes over all the exponents, and I'm checking the bit to see if it's 1 or 0. If it's a 1, that's a power of 2. So here, a 1 at the position 0 means that 5 consists of 2 to the 0, and then a 1 here means that this is 5. So that means that it consists of these 2 powers of 2. So I'm interested in the exponents because that's what I need to use in my table. So I want to jump to make a jump with exponent 0 and a jump with exponent 2. So this is making a power of 2. Is shifting the bit to the ith position, and I'm checking if it is on in k. And if it is on, it means that I want to make a jump of 2 to the I from the current node. So I make the jump, and I am now in a new node. I do that for every power of 2. So this seems right. So are we shifting to the 0th ancestor first? Shifting. So I goes from 0 to 15 inclusive. We're shifting the 1 to the ith position, and we're checking if that bit is on k. If the bit is on, we make that jump from the node. Yeah, I think it's a little confusing that I'm using the same. Let's use E here like I use. So this is an exponent. And so what is my bug? We are returning so here we are at 3, and we want to return the 5th. 0, 1, 2, and 3. Yeah, sure. So we are at 3, and the ancestor is this, and then we go to this. Oh, I know what is my bug. Yes, there's a problem with the -1. There is a problem with the -1, the -1s, because when we jumped outside of the tree, so if we go up too far, we're going to get a -1, and then when we try to use that as a successor, as we want to get the, we're doing something here. This is the double-edged sword of Python, because you can use a -1 index. That's why this doesn't crash, because we are accessing to the -1 position, I think, here. So how can we do this with elegance? So one idea, one trick usually is to make the parent of the root its parent, and that will ensure that you never go outside the tree. The problem is that if you need to then distinguish if you are at that case, and I don't think you have the information if you do that. Do we have to add an if statement? I don't like if statements if I can avoid them. So here, if node is -1 at any stage, we can just return -1. But we need to also take care of this case. Maybe we can add like a special node and make like node n and make the parent, to make that the parent of the root, and then if we get that as a result, we change it by -1, because that's, I mean, we cannot use -1 easily because we cannot index the table with a negative number, but yeah, I think that should work. So let's save n. Let's make this larger. And here we want to overwrite the ancestor of the root, the parent of the root, as n. we don't have any -1. And here, if node is equal to n, we return -1, otherwise we return the node. Let's see if this solves it. List out of range. We increased the size of this. Oh yes, we have to make also the node. Yes, we have to. Yeah, let's say this. We want the parent of the root to be n. We want to ignore the -1, and we want the parent of this a special node to be itself. So okay, it passes the second example. And it accepted. Cool. So yes, this was a nice trick. I think it was elegant, and I didn't have to write an if statement. That's big brain stuff. Well, I mean, I had an if statement at the end, but that is just a translation. But we did not have to have extra if statements in the core of the algorithm, so that's usually a good thing. But what we did is, so this was the root of the tree, and let's say that we have a tree like this. We know what the parents are, but we added an imaginary node. How can we call this? Like the God node. I think in programming it's called Sentinel. It's called a Sentinel when you do this kind of things. So we added this edge, dummy node. Yeah, dummy. But I think on the CLRS book they use the name Sentinel. And we added this edge. We made the parent on all the ancestors of the dummy node itself. So that guarantees us that when we go outside of the tree, we are going to always land on the dummy node, on the Sentinel. And that's how we dealt with that edge case. So yes, I think the code is pretty clear, and I think I covered everything. Let me share the code if you want to check it out. So this technique works. It's pretty useful in general for tree problems. Notice that this is not necessarily a binary tree. It can be any number of any arbitrary tree. It is a rooted tree. And so this is useful also to find the LCA quickly. For all these query problems, there are many problems where we are asked queries of distance between nodes in a tree, or between pairs of nodes, or the LCA. And this can be used to find the LCA quickly, because we can use this trick of jumping to the node, to the root, finding the LCA, and then we can quickly find the distance between two nodes in logarithmic time. So this is useful for many type of problems. So the LCA is the lowest common ancestor, which is a very important concept in trees. But I can explain that in another stream. So I think that's it. Do you have any other questions? This is a problem. I think it was, yes, I'm looking into problems of this level of rating. It was a Q4 in a contest. Had to revisit the bot. Yeah, sure, it's gonna be available. Yes, I need to. I keep saying that I need to create a YouTube channel, because I think the bots are not permanent, but I think these classes can be useful as a reference. So I eventually are going to do it. I'm going to do it. So yes, this was a Q4 in a weekly contest. The rating is 2100. But yes, it's a very well-known problem and a known technique, and now you know it. So cool, that's all I have for now. See you guys. Thanks for the support. Bye bye.